Well, hello and welcome. This is Mr. Robinson back with yet another math video. I know it's been a while. I'm actually going to be coming back, hopefully in full force, during this year as I have some new content to cover again. What I'm going to be doing, this is not AP Calculus at all, but for people who are potentially entering calc or maybe even pre-calculus, just a couple of nice prerequisite practice problems that are algebra based. I'm going to go over, I believe there are only 11 problems here total. The first 5 or so are regarding factoring, and then you have composition of functions and function notation use. I think it's essentially in this order, factoring first. These are kind of combined second. So just a few problems to go over here. This is a nice way of entering into calculus, just some good pre-knowledge. I might mention why in some short aspects. Otherwise, things that you've probably seen before in some capacity or just got to practice again. Okay, so the first 5 here, they are all factoring. The first 3 are polynomials. This one, I guess, essentially could be 1. And then we have some, not technically a polynomial, but something to factor there. Factoring completely is involved by doing several things. For one, you're going to look for common factors. If there's a greatest common factor of something, pull that out of there. Another one, if you've done quadratic factoring before, draw yourself a little diamond or whatever you want to do there. I might try that, for instance, with problem number 3 if it's factorable. I haven't done it yet, so I'm not sure. I do want to try mental factoring on one of them. If you've done that before, it's kind of neat. And then, that's kind of it there. But then you look at problems number 1 and 2, and we notice that we don't quite actually have quadratic factoring, nor do we have a greatest common factor for either of these, really, actually. Let's start looking at number 1. I can't factor out an x. This is a 1 that's in front of that x cubed and such, so we have to find another way of going about it. This is considered a special case of sorts, and this is called a difference. No, excuse me. There's a difference and a sum of 2 cubes, where actually number 2 is going to be a difference of cubes, and number 1 is actually a sum of 2 cubes. And they have kind of a formula to them. I'm not going to spend time doing really a proof with them, but you can always distribute it and find out, or divide and find out, see if it works. This first one right here, if you have some sort of perfect cube expressed in your first term, perfect cube expressed in your second term, like those two, I'll go back to those once I have it, and you are taking the sum of those two terms, you can actually factor this in a way. This does factor into a plus b times the quantity a squared minus ab plus b squared. Okay, so that one's expressed like that. Difference of 2 cubes really falls under the same ilk as sum of 2 cubes here. Instead, you have, though, 2 perfect cubes, and you are taking the difference between them this time. And it's going to look very similar, as I said. Instead of a plus b, though, you're going to have an a minus b. And then right here, it's just a couple switcheroos here. Instead of minus ab, you got a plus ab, and then a plus b squared, just like that. So still a plus b squared right here. The plus becomes a minus plus, whatever, something like that. So I'll be exploring both of those for numbers 1 and 2, using those, and it's a good way of going about it here. So for problem number 1, your identification when they're asking you to factor, we identify that it is, in fact, 2 different terms that are non-factorable in any other way except for the sum of 2 cubes principle. So the way I'm just going to rewrite this to represent what a and b truly are, your a value is really just this x right here. This is x that's being cubed, and then plus, this is a 2 that's being cubed. 8 is also 2 cubed. So you can tell that a is x and b is 2. So we can rewrite all of this using x and 2 instead in their proper format. I'll start off with kind of raw form here. This equals x plus 2 times, we're going to have x squared plus, x squared minus x times 2, notice that b is 2, plus 2 squared. And of course, this can clean up some. This turns into x plus 2 times x squared minus 2x plus 4. And that would be it. That's how we factor that thing there. Now, you might ask the following question. Can this quadratic be factored? And actually, the answer is not only no, but if this were an equation, if this said equals 0, and if you were to solve this thing equals 0 and you factored to get this thing set up because it's an ideal way to go about it, you'll get a solution here of -2. Not only is this not factorable, this will never, ever yield real solutions. There is a complex conjugate pair. You have two imaginary solutions right within here. They are never going to be real, and if they're not real, nor even rational, that means this is never factorable. So you're actually done at that point there. You have to make sure that you pulled out any common factors first from here, which there weren't any, but alas, there we are. We're finished. Okay, number 2, 27x cubed minus 125y cubed. You know, the same kind of thing as before. You might want to first look and see if there's a common factor. Like 27 can divide by like numbers like 3 and 9. 125, to my knowledge, cannot. 125 is factors of like 5 and 25 and stuff like that. So no common factors within the numbers, two different sets of variables, x cubed and y cubed. However, it is still a difference of two cubes. If you can identify what you are cubing in here, what number do you cube to get 27? What value do you cube to get x cubed, you know? You'll figure out, hey, 3 cubed becomes 27, and of course x cubed is x cubed, and that represents my, for difference, a value. Minus, same kind of thing right here. What do I cube to get 125? Well, that actually happens to be a 5, and then y cubed, of course, becomes y cubed, and so 5y becomes b. So that right there, we'll put equals and equals. So that right there we can separate it right here. That becomes a minus b. Keep in mind, your b is not -5y, it's just +5y, but we are going to subtract our b value times, I'm going to put in parentheses first, a squared plus a times b plus b squared, as follows. Okay, that's in raw form. Let's clean it up a little bit more. 3x minus 5y will stay as is. No common factors in there, of course. 3x quantity squared is 9x squared. Make sure you square that 3 as well. That's why parentheses are so super important for this. 3 times 5 is 15. X times y, we get xy. And 5y quantity squared becomes 25y squared. Once again, no longer factorable after that. That's as deep as you can get. Sorry for the little offline drawing. That's as good as you can get. This has no other such factoring within that we can do or manage. And again, no real solutions within that bit either. And this has two different variables. Not much you can solve anyway. We're not solving, we're factoring. Okay, number 3, actually more simplistic, I would say, outside of the difference in sum of two cubes aspect. I'm going to seek a common factor first. And it looks like although no numbers can be factored out, I can definitely take out two multiples of x. In both, two powers of x, not two multiples. Two powers of x from all these things here. So I'm left with 2x squared plus 5x to the first power minus 3. Now, unlike this one, I shouldn't just say, oh, let's box it, we're done. I should look to see if this quadratic can be factored. And off the top of my head, yeah, it can. Off the top of my head, I'm getting that. So here's my mental factoring. If I'm going to impress some bunch within here to go like, oh, I wish I knew how to do that. How did you do that? So there it goes. It looks like that. Now, how did I do that? Let's look at a quick mental factoring thing, then I'll shut it down. I'm going to rewrite that, just this part here. Notice what I wrote to begin with. I started with this. Now, why did I do this? Because factoring is the opposite of distributing. And when you distribute, like this quadratic thing, you're expecting to have it have been factored into two different binomials multiplying. So I know there's going to be a term here and a term here, and essentially you're going to do that FOIL method. You know, this is going to happen here. You get first terms, outside terms, inside terms, and last terms multiplying. But notice how I started my first terms. 2x multiplies with x to give me 2x squared. There's no other way to do that. There's no other way to get 2x squared other than multiplying 2x with x when it comes to this sort of binomial multiplication distribution. such stuff. So what was left for me to do was figure out, you know how the last terms give you this -3, for example? I need to figure out what numbers here can give me -3. I could do -3 and +1, or +3 and -1, or +1 and -3, or -1 and +3. Now there's a big difference between all of these. Let's work at +3 and -1 to start. There's a big difference because it depends on which multiplies with what. My x is not going to multiply with this -1, but my 2x is. 2x times -1 is -2x, and x times 3 is 3x. -2x plus 3x is 1x, but I'm seeking a positive 5x. What kind of thing can I multiply together and then add to get a positive 5x? And the one that worked out, you can tell, is this -1 and +3. Take a look at this. 2x times 3 is 6x. X times -1 is -1x, and 6x minus 1x does give you that 5x. That's the mental factoring approach that I do, and thankfully those were prime numbers, the 3 and the 2, the -3 and the 2. Once they become composite numbers, it's a little trickier. How else can we do that? Because it can lead into this one a little bit. There's something with a kind of a diamond method and factoring by grouping. Let me lend into that. Not going to teach it, so to speak, but I will go through it. I'm trying to find two numbers that multiply to become -6. I got to multiply the 2 with the -3 here, and I get -6, and find two numbers that add to become 5. Again, not deep in the explanation today. Just going to play with it in this aspect right here. So I should be doing what? 6 and -1. 6 and -1 there. And then what I'm going to do is I'm going to rewrite this trinomial to give instead a positive 6x and a -1x. 6x minus 1x is 5x. That's what these two numbers are representing right here. And then -3. So I rewrote this trinomial into a quadrinomial of sorts, even though these two would combine to become -5x or positive 5x. But the goal is to split it, because what I'm going to do is this factoring by grouping stage, and I'm going to do this as well in number 4, so pay close attention. I'm pairing up two sets of terms right here, and I'm going to figure out what the greatest common factor is of both sets. 2x squared plus 6x, the greatest common factor of that is 2x, and left inside is x plus 3. Now, even though you might state there's no greatest common factor here, my end goal will be to get another x plus 3 left inside after I factor whatever out of this, even if it was a 1. In this case, factoring out a 1 would leave me with -x minus 3, but if I factor out a -1, notice that, -1 times x is -1x, -1 times 3 is -3. That leaves me with x plus 3 there as well. Why is this important? Because now x plus 3 is a common factor in both of these sets of terms. And that really is ideal for us, because if I can factor out that x plus 3 from both terms here, what's left for me is 2x minus 1. I know people get really troubled with this perception right here, what's going on. I do have other videos that express this in greater detail, but notice I am just trying to get the same answer here as I did here. Now, the full factorization leaves the x squared. Don't leave that out. I was just working on the quadratic factoring right here, spilling that one out, but the x squared should also be taking form in your final answer. And of course, there's my final answer there. Sorry for the long description. Now, I'm going to be doing factoring by grouping one more time with this as well. You look at this and you go, oh, geez, there's 4 terms, none of which can combine, because there's nothing that's fully alike. Even though these both have C and these both have B, or these both have A, or these both have D, nothing can fully combine here, at least not at this current moment. But what I will do if I have a quadrinomial right here, 4-term polynomial, is I will check the factoring by grouping stage. Are there at least common factors within pairs that will leave me with literally common factored portions within those sets of both terms? Like here, the x plus 3. Let's check it out. C is a common factor in both of these terms. If I factor out, I'm left with a plus d. Wouldn't it be nice if I could factor out something here and be left with a plus d as well? Let's go ahead and make the small assumption right now that you can do it, because I do see an a and a d and a common factor of b. So if I factor out a b, but not just any b, a negative b, notice how that will leave me with a plus d inside. Negative b times a and negative b times d would give me that. So this is good. This is huge because a plus d is now a common factor of both of these terms, of this term and of that term. And if I factor the a plus d out, maybe it'll make most sense this time if I factor it out in front. If I factor the a plus d out right here, I'm left with c minus b in those terms after I've factored out a plus d. Now, I'm not going to go over this in great detail again, but a lot of people ask, where did the other a plus d go? Where did the other x plus 3 go? It didn't go anywhere. It factored out, much like c factored out of here. You know, you don't ask where did the other c go. It factored out, and a plus d is what was left. I factor out a plus d, and c minus b is what was left. And that's a decent enough answer for myself, and I think I'm good with that. So I'll stick with that. We're done. That is full factorization. Okay, number 5, we want to factor out here. Before I deal with the x stuff, let me just take care of the 2 and the 6 right here, the negative 6. There is a greatest common factor within those numbers. A 2 can factor out of both terms here, left with a square root of x in one term and a minus 3x to the 3 halves in the other term. My phone is just going off. Let me turn this thing off for a moment because I'm getting multiple texts here. That's very unconventional of me. Sorry. Okay, so factored out a 2. Now keep in mind, that's part of it, but that doesn't mean you're done. Factored correctly, not necessarily completely. How can I deal with this x stuff, especially when they're represented so differently? Well, at some point, especially if this is an AP Calc prereq review, at some point you've probably learned somewhere along the way that the square root of x can also be written as x to the 1/2 power. And I think it's nice to do it that way for a couple reasons, mostly because that way your other x that's going on, right here, that is a fraction exponent, can be kind of represented alongside it. It's kind of nice that you can get two things that are kind of written, in the same fashion there. Now, you might not be sure what to do here next, so to speak, but I want to pay close attention. I want you to pay close attention to what happened when I factored out this x squared. When I factored out x squared, I was left with x squared here, x to the first here, and technically here, x to the 0 power. Of course, x to the 0 power is 1, it goes away. But this 2, 1, and 0, before they were 4, 3, and 2. I took out 2 powers of x, and we were left with 2 from 4, 1 from 3, and 0 from 2. So we removed 2 powers of x. We subtracted from here. Now, these both have halves from here. So if I removed a half right here, this x to the 1/2 power, well, what's left in here? It's just 1, but what's left right here, the 3 still there, what is left here after I remove half of a power of x from this one here? We got to do 3 halves minus 1/2. That's what's going on right here. And 3 halves minus 1/2 is 2 halves, or just better written as 1. Just 1 right there. I factored out this 1/2, and of course there's nothing left there but the 1. And then here, when I removed 1/2 of a power from the 3 halves, I subtracted 1/2 from 3 halves, and you're just left with 1. That's very good to look at. That's good. Now, if you want to bring this all the way back, if you look at an answer key for a question like this, I'm willing to bet they bring it back to a square root of x. Remember, x to the 1/2 power is the square root of x. And right here, x to the first power is just better written as x. So you can just write it like that, and you're all set. 2 root x times the quantity, 1 minus 3x. And by and large, I'd say that is also completely factored. We're all set to go. Okay, moving on. Now we're going to get into composition of functions and function notation. Every problem within here essentially will ask you to substitute some values in for x and get a final evaluation. Some are left with variables still within. That's totally fine. Just keep in mind, whatever they're asking you to substitute for x, do a direct substitution. I would recommend parentheses to start with, and then go on from there. Okay, we're given that f of x equals the absolute value of x minus 3, close that quantity, and then subtract 7. We need to find f of 1 minus f of 5. F of 1 just means find the value of this. Remember, f of x is y. It means find the value of y when x is 1. So we're going to substitute. I'm not going to do a full expression here. I'm just going to start with f of 1 and then I'll also do f of 5, and then I'll combine them both together. F of 1 is substituting in 1 for x minus 3, take the absolute value of that, and then subtract not 3, but 7. That equals 1 minus 3, which is negative 2. Absolute value of negative 2, all that minus 7. The absolute value of negative 2 is 2, and that minus 7 is negative 5. Not done with the answer, of course, because we also got to do f of 5, and then we got to subtract the result of both of these things. F of 5 is 5 minus 3, all minus 7. And that equals positive 2 in the absolute value, minus 7. Absolute value of 2 is still 2. Minus 7 is negative 5. So what we have to do is we have to take f of 1 minus f of 5. F of 1 minus f of 5 gives us negative 5 for f of 1 minus, notice this minus here, negative 5 for f of 5. That becomes negative 5 plus 5, which is 0. So f of 1 minus f of 5 is 0. That is the difference in heights between these two things on a graph. If you graphed this, the value of y at x equals 1 is negative 5. The value of y at x equals 5 is negative 5. The difference in heights between them is 0. Bada boom, bada beam. Number 2, find f of x plus 2 minus f of 2 given this quadratic function for f of x. So this one's a little different because there's a larger quantity inside here and a variable. But, you know, again, if you just do this one bit at a time, I think you'll be a lot more organized with it. You'll probably feel better with your result, not cramming everything together. Let's start with just f of x plus 2. Now remember, this will take place of the x that's inside right here and right here. Basically, an x plus 2 will take place. And it's very important that you use parentheses here because we have to make sure that we square all of that which is taking place of x. A little bit of redundancy because there's an x within here, and that, or not redundancy, recursion, because there's an x within here and then an x right here, but they are different terms, and we have to apply it as so. So this x is being squared, this x is being multiplied by negative 3, that x plus 2, and then plus 4. Now, x plus 2 quantity squared is not just x squared plus 4. Remember, it is x plus 2 times x plus 2, and that becomes x squared plus 4x plus 4, minus the negative 3 will multiply with x, and the negative 3 will multiply with 2. That is a negative 6. Don't put plus 6. I know a lot of people do 3 times 2 there. Even calc students, plus 4. Well, pre-calc students at least. I've tutored some calc students that might accidentally do that time to time, but they seem to be better with their habits over time. All right, no other x squared, so that's just going to be there. 4x minus 3x is 1x, and 4 plus 4 is 8. So that becomes x squared plus x plus 8. F of 2, just f of 2, is going to become, let's see, 2 squared minus 3 times 2 plus 4, which is 4 minus 6 plus 4. That's negative 2 plus 4, which is 2. So we have x squared plus x plus 8 for f of x plus 2. F of 2 is 2. We are going to subtract those two bits. F of x plus 2 minus f of 2 will give us x squared plus x plus 8 minus 2. 8 minus 2 is 6, so we get x squared plus x plus 6. That is the result of that set. Substituting those in using function notation, etc. Okay, numbers 3 and 4. Find f of x plus h given this. And you see another f of x plus h thing right here. When you're starting to use h, I don't want to get too deep into it, but you'll normally be using it as h gets really close to 0, basically x, but a little bit farther away, because it has to do with dividing by close to 0, but not actually 0. Something you'll start learning in calculus. You start by calling it the limit process, and then you move on from there. So get used to this. This isn't just for these problems, and you're like, phew, I'm done. Not that they're necessarily difficult, but make sure you keep everything in good order. So number 3 here, f of x plus h, let's just do it all in one swoop. We are substituting x plus h in for x. So x plus h quantity squared plus 2 times the quantity x plus h plus 1. X plus h quantity squared, it is a perfect squared trinomial like the last one. It is x squared plus 2xh plus h squared. Going to save you some time on that. Plus 2x plus 2h when I distribute that, plus 1. Can anything combine? I don't think so. You could go for some common factor stuff. I don't think it's going to really get you much of anywhere. I don't know that for sure, but this was factored as is in a way, and I think that's kind of going to be it for this problem. You're going to get a little deeper into these problems than just that. I think it's to help you practice for this one that's coming up, just so you're well versed in what happens. I'm good with that answer. That's all we can do. Number 4, find f of x plus h minus f of x over h, given this such and such here. And again, this stuff has to do with, it starts to plug in, it's called the limit process. This helps you provide what's called the instantaneous rate of change, or derivative. Once you hear either of those two terms in your calc class, you'll say, Mr. Robinson said it first. He didn't make that up. It's true. All right, so same kind of stuff here, only I'm going to separate the workload, and then I'm going to put it all in together just so we don't make any mistakes. Probably good practice. 3 times x plus h quantity squared plus 1. Notice you do not distribute the 3 into here before you square it. You got to square this thing first. Order of operations. X squared plus 2xh plus h squared times 3. All that plus 1 gives you 3x squared plus 6xh plus 3h, not x, squared plus 1. And that's as much as I can do with that for now. F of x, of course, is 3x squared plus 1, so I guess I'll leave that as is, and then h is just h. Now, what's going to happen with these problems here, you're going to see is we are actually going to aim for and find a way to eliminate this h. It's for something that, again, you don't want to divide by 0. It's something that you'll do. Maybe not all h's will cancel, but the bottom one we are attempting to do. So, all this together, here we go. F of x plus h is this guy right here, 3x squared plus 6xh plus 3h squared plus 1. We are going to subtract f of x. Now keep in mind, f of x is the entire quantity. So it's not just minus 3x squared plus 1. You got to make sure that you wrap it around parentheses, so the 1 will also be subtracted in the end. This is all divided by h. Now, right here, this will be 3x squared plus 6xh. The only problem I really have with these problems is you got to keep rewriting this stuff over and over. That's why I didn't want to do this part over and over. Just want to do that separately. So minus 3x squared minus 1 all over h. Now, an interesting concept, again, that'll happen here, especially with just the polynomials that aren't too tricky. 3x squared minus 3x squared actually appears here. These can cancel. And 1 minus 1 appears right here. This can cancel. All that will remain on top are terms that contain at least a single multiple of h. This is good, because this means, and I'm going to rewrite this so the quadratic is first. It's just a little OCD thing. I can factor out a multiple of h right here. Therefore, then I can make them become 1. I can cancel out the multiple of h on top and bottom that exist as common multiples. So if I factor out the h on top, I'm left with 3h plus 6x all divided by h. And these h's right here do divide and cancel and become 1. So you're left with, you know what, now I kind of want that x first. So I'm left with 6x plus 3h right there. And again, when you start doing this in calculus, maybe some bits of pre-calc, at this point you actually get to substitute 0 for h for a specific reason. You're going to do something with that. Again, instantaneous rate of change and or derivative. Those two terms are rather synonymous. You will learn those two words in calculus. That's your answer. That's your end result. I know this one didn't clean up very good and dandy, but that's because you didn't have all this other stuff along the way. This one cleans up significantly better. All right, last two problems here. This is a composition of functions. So what you have is f of g of 2, f of h of negative 1, and you're given these functions right here and what they have, what you do of them, yada, yada. There are two different ways to go about it, kind of your call. One thing is to do g of 2 first. and then do f of whatever the value is that you do. I'll do both of these in, let me think about which way I want to. Yeah, I'll do both of these two different ways. I'll do this one way, I'll do number 6 another way. It's up to how you want to do that. But you do work from the inside out. I'm going to figure out what g of 2 is. It'll become some value. So that's 2 times 2 minus 1. 4 minus 1 is 3. And that's what we're taking f of. We're taking f of 3. G of 2 is 3, right? That's what we're doing. So here we go. What is f of 3? We look at f of x's equation. That's 3 squared plus 3, which is 9, plus 3, which is 12. So f of g of 2 is 12. That's what that end result becomes. So that's one way to do it. It's more often the preferred way for people, especially if these were small enough numbers. The alternative way to do this is to do this. Let's find out what f of h of x is first, meaning let's clean up those two together. So h of x is 2 to the x power. I'm going to substitute 2 to the x power in for x right here, and then that's what f of h of x is. And then what I'll do is I'll substitute -1 into that final result. So this becomes 2x, 2 to the x, quantity squared, plus 3. The other reason I'm doing this is because I want you to see a property, which becomes 2 to the 2x plus 3. Now, you also could write 4 to the x plus 3 if you wanted to, because this is 2 squared to the x power as well. Hopefully you know that property that not power to a power, but this quantity raised to a power, the exponents will multiply, and multiplication is commutative, so I could then reverse this process if I wanted to. So 4 to the x plus 3 is f of h of x. So now let's find f of h of -1 just by substituting -1 right into here, and then I'll be set. That's 4 to the -1 plus 3. That's not -4, that is 1/4. And 1/4 plus 3 would be either 3 1/4, or 3.25, or my most preferred answer to this is 13/4 as an improper fraction. I like that one the most. I think you'd see that most often with things. But that ends up being your final result. Again, you could have substituted -1 in for h of x right here immediately, and then plugged in that 1/2 answer into there. That would have been fine. I chose to do it a different way. All right, so that's it. Those are your practice problems. You saw a couple things there. I might do some other videos along the way with this. But again, keep in mind, I'm going to be doing more YouTube videos in the near future, likely for algebra and geometry, because those are the kinds of classes I'm teaching again this year. Maybe if I teach a calc class again in the future, you can have fun exploring that. But yeah, I'm going to be coming back to my YouTube channel doing a few more videos for you guys in the future. Fiend!